Good evening, dear viewers and my dear students who are watching this program. My teacher, which is the UAE's biggest classroom. Today I am here with you to discuss a few things about 12th standard physics. So, I request the 12th standard students who are watching this program, you can listen to it and you can keep a notebook and paper, because you must be busy in the preparations for the terminal examinations coming up. So, all of you are ready, I think. So, anyway, my plan today is initially I will explain a few things in connection with the chapter magnetism, and further a few things I will explain first in the first part of the session. Then we will move on to some important questions based on the examinations, board exams. So, let us see, and at the same time, while you are preparing for the examinations, if you came across any sort of difficulties or problems, numericals or anything of that sort, if you have, you can call us right now, because this is the time for you to call and find out what all call and clarify your problems, doubts. So, this is it's a live classroom. I know all the UAE is the whole UAE is watching this program, and I understand the 12th standard students are right now there with me, and even otherwise also, like those who are not in 12th but they are in 10th, 11th or 9th. If you have any confusions about physics, you can very well get back to us. Any doubts, if you have, if it can be sorted out now, we can do that now itself. Otherwise, we will make a note on this and we will discuss in the next session. Whatever it is, it's your program. You get back to us if you have any confusions. Okay. So, with that note, without spending much of time in general, we will straight away move on to be specific on certain topics of the chapter magnetism. First, I will show you certain things, like you must be familiar with or you might have done in the class the concepts of force on a moving charge. It's in fact a very important section, in the sense you have to have a very clear picture about how a charged particle is moving in a magnetic field. And of course, there are many short questions, numerical problems, descriptive type questions. Descriptive type questions, based on that, is nothing but the cyclotron. Must be familiar with that. All these are really significant as far as the exams are concerned. See, in the first unit of physics, you studied the movement of charge in an electric field. What happens when an electric field is applied and when a charged particle is made to enter the electric field. We have seen that. This unit, we are talking about the movement of charged particle in a magnetic field. So, one basic difference I will tell you. This is the basic difference. Just imagine you are keeping a charged particle inside a uniform electric field. So, what will happen to it? If you keep a charged particle in a uniform electric field, straight away the charged particle will accelerate, right? Acceleration of charged particle will be there. That is, it will gain kinetic energy. This is what exactly happening when a charged particle is in an electric field. You know the equation F is equal to QE. See, F is equal to QE is the equation we have for charged particle in an electric field, force on the charged particle by the electric field, F is equal to QE. Okay, but if you do the same thing, that is magnetic field, if you do, that is in the electric field, you kept the charged particle, we found that it is accelerated, it is gaining kinetic energy. But if you do the same thing with a magnetic field, that is, a charged particle is just released in a magnetic field, you are keeping the charged particle in a magnetic field, what will happen? Nothing will happen. It doesn't move, it doesn't accelerate. So, that is the basic difference. That is, as long as the charged particle is inside an electric field, it is accelerated, or it is gaining kinetic energy, speeding up, we can say. Whereas, as long as a charged particle in a magnetic field, it is not necessary that there should be a force, there should be an acceleration, there should be increase in kinetic energy. Then what is the difference? You must be familiar with another equation, that is F is equal to Q V cross B in the vector form. Okay, the first equation in the vector form is this one. This is force by the electric field, this force by the magnetic field. So, what do you make out from this is the force in the magnetic field, sorry, electric field, that depends only on Q and the strength of the electric field, whereas the force by the magnetic field depends on Q, V, B and even theta, because V cross B is VB sin theta. So, theta also is a factor. So, in that case, otherwise we can, in magnitude you can write it as what, QVB sin theta. So, that means the force experienced by the charge particle in a magnetic field, that depends on the quantity of charge. Suppose, imagine the charge, this is what I said at the beginning, if a charge particle is released, that is at rest, okay, it is at rest, means velocity is 0, no force. Another thing, if the charge particle is moving parallel to the field, that is theta is equal to 0, or it is anti-parallel to the field, that is theta is equal to 180 degree, sin 0 or sin 180 degree, 0 only, there again force is 0. So, there was a one more question in one of the board papers. The question was this way, a charge particle is moving in a region, okay, moving in a region of space, is and further it is given the charge particle goes without any deflection. So, once again the charge particle is kept in a or it is in a field region, in a region, and goes without any deflection. If it goes without any deflection, is it necessary that there is no field, no magnetic field, no magnetic field? If it goes without any deflection, is it necessary that there is no magnetic field? Answer is no. It is not necessary, because there may be a magnetic field, but the charge particle may be moving parallel to the field, that is theta is equal to 0, or anti-parallel to the field, that is theta is equal to 180 degree. These two cases there is no force, that means there won't be any increase in kinetic energy. Alright, so these are the areas you should be clear about: force by the electric field, force by the magnetic field. Okay, so now I will show you, we will have a quick review through the whole content. If the charge particle is in a magnetic field, there is, say you can see the equation, the basic equation is F is equal to QVB sin theta, in the vector form is Q into V cross B. We will just have a look at the quick review of the contents we will see. Okay, 1 Tesla definition, then there are 3 different paths. The first path is when the charge particle is parallel or anti-parallel, there is no force at all, it will go in a straight line itself. Okay, then second part is again important, that is, it says when the charge particle is in a magnetic field moving perpendicular to the field. See, look at the second case, it is moving perpendicular to the field. How the case is, it is gaining a force, that force is used up to provide necessary centripetal force, that is what is shown as mv squared by r is equal to qvb. Okay, so it shows that radius is directly proportional to the momentum. This part is again a very important concept which we will make use of in short questions. And the next one, you see the third trajectory. Third trajectory is it's at an angle which is lying in between 0 and 90 degree. See, it is an arbitrary angle, you can make out that 0 and 90 degree. So, what you can make out? It can be considered as a combination of the initial, that is along this, that is at an angle when it is entering, there are 2 components. You can clearly see, look at this picture. So, you can see this part, the velocity is resolved into 2 components, Vx and Vy. X component is along the direction of the magnetic field, so there is no force due to this, so it will go in a straight line. Y component is perpendicular to the field, so it will move in a circular path. So, it has got both circular motion and straight line motion. It moves forward as well as it is moving in a circular path. Circular path means its radius you can calculate using this equation, r is equal to m into v sin theta, only the perpendicular component of the velocity we have to make use of. Then pitch means, this distance, I think you can see this part. So, this distance, the horizontal distance travelled by the particle by the time it makes one revolution is what is called pitch. Pitch you can calculate using this equation, P is V cos theta times t. The capital letter T is what is indicating the time period of revolution. Okay. Then this is what is made use of in cyclotron. Cyclotron, what it is, that is a device used to accelerate charged particles to a high speed. Okay. Then there are the principle we have seen. There are 3 points you can write under principle. Then see, this is the picture of a cyclotron, you can clearly see. See, look at this part. This is the position, the center of the cyclotron. This is the position where the charge particle is released. So the frequency, see, look at this part. Okay, it's an oscillator, we say. Okay, this one, oscillator, this part. Okay, so in this oscillator, this is what is producing electrical oscillations. Okay, this oscillations, if it is in such a, it's adjusted, the frequency is adjusted in such a way that is equal to the frequency of revolution of the ion inside. Meaning, then what happens is, just imagine the moment you release a positive charge over here, at the center, the moment you release a positive charge here, this D is negative, let's say. Then what happens? Quickly it will be attracted or accelerated towards it. Then the frequency of the oscillations of the oscillator should be adjusted in such a way that by the time it comes out the D, polarities should be reversed. So what does it mean? That is, this D becomes negative now, the other D becomes positive. So it will be quickly attracted towards this one. But it is increasing its velocity, so it is gaining more radius path, so again it comes out. So every time it comes out, the basic point to remember in cyclotron is, the moment the charge particle comes out of the D, the frequency should be adjusted in such a way that the polarities of the D should be reversed polarity. So it will be quickly accelerated. So one more thing you can make out is, look at the gap between the two Ds. So this gap is what is in fact only in that place there is gaining of kinetic energy happens. So always remember, kinetic energy it gains only when the charge particle is inside an electric field, not inside a magnetic field. Inside magnetic field there will be force, but that force is utilized only to make it move in a circular path. Okay, so this is a picture of a cyclotron. Be very clear about that. This is actually the diagram given in the textbook. So you can, this is the diagram which you are supposed to draw in the exam. The what all things to be shown clearly, the detailing is, it should be a label diagram. These are the two D's. This is the gap. This is the place where the charge particle is released. At P oscillator it is connected, and finally after getting continuous acceleration it will come out like this through the exit port. So this is the place where we are getting a very high energetic charge particle. That's why it is a particle accelerator. And important thing to remember is the perpendicular magnetic field. You can clearly, if you look at the diagram closely, you can see there are dots shown which indicates there are magnetic fields. Magnetic field, a uniform magnetic field is provided perpendicular to the plane of the sheet, right? So it comes out. So can you say, and at this point of time, let me ask you one thing: what is the condition for resonance? What is the condition for resonance? Resonance means, I just mentioned about this aspect. Whenever charge particle comes out of the D, the polarities should be reversed. How is that made possible? You initially calculate the frequency of revolution of charge particle inside a uniform magnetic field. That frequency is what you calculate using this equation. Equate it with what? mv squared by r, and rearranging the equation, you can prove that frequency is qb by 2 pi m. You see, when a charge particle enters a perpendicular magnetic field, and if its mass is m, then what happens is it will have a given frequency of revolution. So always, how much is the frequency with which with charge particle moves in a circular path? That depends on mass, charge, and magnetic field. Right? So it does not depend on radius or speed or anything. That's the reason why the moment when it enters with a higher speed, it will tend to go in a bigger radius path, because the time period or frequency of revolution is adjusted to be the same. So what I was asking is, what is the condition for resonance of cyclotron? Resonance. Resonating something, matching. What is the concept of resonance? This is frequency of revolution of charge particle inside a uniform magnetic field. Initially, if you adjust the frequency of the oscillations from the oscillator, I showed you the oscillator. No? So in that oscillator, you adjust the frequency. Frequency can be adjusted. The frequency of electrical oscillations that is provided by the oscillator to the D's should be such that that frequency should be equal to what? The frequency of the revolution of the charge particle inside the magnetic field. Sorry. So the frequency of revolution of the charge particle and the frequency of electrical oscillations from the oscillator should match or should be equal. This condition, if you can adjust it like that, this condition of cyclotron is what is said to be the resonance condition of cyclotron. So, when can a cyclotron said to be at resonance? Can say cyclotron is said to be at resonance if the frequency of revolution of the charged particle inside the field is the same as the frequency of oscillations from the oscillator. Is it clear? All right. Now, again you look at the diagram, you can see the on the screen the cyclotron, the limitations I have seen, we have seen the limitations. All right, these are two limitations we have basically. Just have a look at, all of you must be familiar with that, and the uses. These are the points you should be clear about as far as the exams are concerned. Okay. Now, some general aspects, you might have heard of the experiment which is being conducted in CERN, okay, in France, okay, or in Switzerland. Okay, it's in the border between Switzerland and France. So, in the CERN is exactly at Geneva, right? There the experiment is being done. This experiment, they are making use of a number of particle accelerators. Okay, one of the illustration about the particle accelerators, you can see it over here. You have a look at that. Okay, so this is the trajectory. The trajectory will be made to become in a bigger one, so it will be made to move more and more fast. This is one of this, what is marked as ATLAS now, that is one of the particle accelerators which is situated in CERN in Geneva. Okay, so that is one thing. Then this is actually the picture of the accelerator which is kept in CERN. Okay, it is one of the particle accelerators. You might have heard of the underground particle accelerators used for the acceleration of charged particles. So, for that only we are making use of this cyclotron. Okay, you can see this is one of the underground accelerator in CERN. Okay, I hope you have seen. All right. Then this picture is one of the old particle accelerators. It was built in 1937, as you can see on the screen. Okay, that's again made in Switzerland. Okay, this is one of the old particle accelerators. Otherwise, it's a French cyclotron. And one more is there. This is another one which is made in Washington. Okay, it's also a cyclotron. It's another model of the cyclotron, another type of cyclotron. Okay, I hope you have seen. Then this expression you can make out using the two equations we have for the calculation of maximum kinetic energy. So, all of you just have a look at the two equations, how you make out. You see on the diagram, on the equation, you can make out one thing. The first part is what? Kinetic energy. This part is showing the centripetal forces provided by QVB, from which you get an equation for velocity. Then kinetic energy, half mv squared, we are getting it. And if you replace this small letter r with capital letter R, okay, what you can see is this. What is the difference between small r and capital R? Small r is the radius of the charged particle and capital R is the radius of the D. The moment the charged particle comes out of the D, the last moment, the radius of the particle is the same as the radius of the D. That is why we are replacing small letter r with the capital R. Have you seen that? That is, I will tell you once again. That is the moment the charged particle comes out of the D. So, that is after continuous acceleration through the exit window when it comes out. At this moment, this is the moment it has got the highest acceleration. Okay. So, that time the charged particles radius and the D's radius, they are the same. That is why in the expression, you can see it on the board again. Look at the screen. You can see the kinetic energy maximum. You see kinetic energy maximum is, see this equation. This is what I was talking about. This is one of the equations for maximum kinetic energy with which the charged particle comes out of the D. And even the second equation also, have you seen that? Maximum kinetic energy is also given by 2nqv. What is that exactly? That V is the potential energy. You have studied an equation in the second chapter. QV is the kinetic energy gained by a charged particle under a potential difference V. So, every time when the charged particle comes to the gap between the D's, it is gaining kinetic energy. So, what is the value of expression for kinetic energy? QV. right. So, in once when it comes out, it gains kinetic energy QV. Again it goes, and when it comes out, after half a revolution, again it comes out of the D. That time again it is gaining kinetic energy. How much? Again QV. So, in one revolution it gets kinetic energy QV. Suppose before the charged particle comes out of the D, totally it makes say n revolutions. Then what will be the total kinetic energy? N times 2 QV. 2 QV is the energy gained in every revolution, because in one revolution it comes twice in the gap. Every time when it comes to the gap, it gains kinetic energy QV, right? 2 QV QV, like the 2 QV once, like that n times. So, that is how we get the equation 2n QV as the expression for maximum kinetic energy, right? Then we have some questions. I will explain the first question. You look at the question, all of you. An electron emitted by a heated cathode and accelerated through a potential difference of 2 kilovolt enters a region with a uniform magnetic field of 0.15 Tesla. Determine the trajectory of the electron if the field traverses the initial velocity. What do you mean by field traverses the initial velocity? Field traverses means field becomes perpendicular to the initial velocity, right. So, what is given over here is a charged particle enters a uniform electric field, but after accelerated under a potential difference 2 kilovolt. That is what is given in the question. Charged particle is electron. So, basically whenever a charged particle enters a uniform electric field perpendicular to the field, straight away what you can write is mv squared by r, that is expression for centripetal force, is provided by QVB. This is the equation we are getting. We have to use whenever a charged particle enters a perpendicular uniform magnetic field, all right. So, the Q now here we can replace with E, right, because it is electron. One V you can cancel. So, what the question over here is determine the trajectory of the electron. Since it is moving perpendicular to the field, it goes in a circular path. Circular path means it has a radius. So, trajectory of the path means trajectory of the electron means find out the radius of the path. So, R is equal to what you will get mv by EB. Okay. So, the mass of the electron is known, charge of the electron is known, the magnetic field B is what is given by 0.15 Tesla. Okay. So, this is the value of magnetic field. So, this V we can find. This is missing in the question, but instead what is given is the electron is being accelerated under a potential difference 2 kilovolt. Once again you have a look at the question, you can clearly see. See, go through that. An electron emitted by a heated cathode and accelerated through a potential difference of 2 kilovolt enters a region with a uniform magnetic field of 0.15 Tesla. So, initially it is accelerated under 2 kilovolt. So, the 2 kilovolt, now look at the board, 2 kilovolt, it's not volt, is that is not V. This V is velocity, not potential difference. So, what we are going to get? An expression for velocity in terms of potential difference, which is what we are getting using the equation EV is equal to half m V squared. Right, half m V squared is the kinetic energy which is provided by EV. So, we can write an expression for velocity as what? Square root of 2 EV divided by m. This 2 EV by m, this is the expression for velocity, right. Now, this V you can substitute here, right. So, this you see the velocity you can calculate using this equation, or what also we can write is, look, I am replacing V with this m by EB, right, root of 2 EV by m. So, in that case if you take this m and E into the square root, what will you get is R is equal to 1 by B times root of 2 mv by E. 1 m and 1 v will be cancelled. You see, by the way, this alone can be asked as a separate question. Prove that the radius is given by this equation. This can be a separate question. Okay, 1 by B root of, I think it is not clear, 1 by B root of this one 2 mv by E. So now you substitute this equation, okay. This the data over here, if you substitute the data given, V is what, 2 kilovolt, V is 2 kilovolt, mass is given, charge is given, then what happens, and magnetic field is given. Substitute all the values in this equation, you will be able to calculate the radius. That is the radius of the trajectory of the electron. Trajectory of the electron means, so you can see that. Now you can see this. Trajectory is 2 mv by E. Clear? Now actually we are into the discussion of concepts of magnetism. Okay, again dear students, if any confusions there, you can very well call us. I am going for a short break. After the break, when I come back, by the time if you have any confusions, you can keep it ready. That is one thing. And second thing, even some questions related to potentiometer also, any areas to be discussed, you feel free to tell us what to be discussed. Maybe one content of another chapter, maybe another question, whatever to be done, whatever to be cleared, you can very well tell us. We will discuss those things. Okay. Anyway, stay tuned. We will go for a short break and come back.